All right, so far, here's where we are. Stop, stop, stop. Lecture time. All right, so we have the ability to predict, hey, we have these starting conditions. We know the equilibrium constant. Where will things end up? The equilibrium constant tells us the ratio of products to reactants. We use Q. Sometimes we solve for X, right? We predict how things shift, how things change over time. Okay. But what we want to do, the next step is, hey, what happens after the system reaches equilibrium? What if we take that system that's at equilibrium and make a change? What if we add some more reactants? What if I take out some products? What if I change the volume of the container? What happens if I change the temperature? Okay. How does a system that has reached equilibrium react to changes? How does the equilibrium shift when I stress it, when I make some sort of change? All right. So we have our chemical reaction that we've been looking at the whole time, the reaction of nitrogen and hydrogen to produce ammonia. Okay. We can think of that as a balancing point, that the products and the reactants end up at some balance where we know what that ratio is. We have the products raised to their coefficient powers divided by the reactants raised to those coefficient powers, and they reach some value. Okay. And that balance, that point is where we are in balance. The forward reaction rate and the reverse reaction rate are equal. The concentrations stop changing. But what would happen if I then take this system in balance and I add a bunch of nitrogen? Okay. So it was at equilibrium and I spike up, I change one of the values. Clearly, the ratio has changed. Clearly, I'm no longer in balance, that the system is disturbed. The ratio of my reactants and products is no longer equal to K, right? Q doesn't equal K. I've changed the conditions. We want to be able to predict, to get back to equilibrium, am I going to end up creating products or am I going to end up creating reactants? And the language we use is, which way will the system shift? Will it shift to the left, shift to the right, shift to the reactants, shift to the products? That's the kind of language you're going to see on the questions that you're going to come across. And what we need to understand and keep in mind, I think, is a look at the rate of the chemical reactions. Because there are two chemical reactions happening here. We've got going from left to right and right to left. And each of those has its own rate constant and its own rate of chemical reaction. And we've talked about at equilibrium, those rates are the same. Okay. If I add a bunch of nitrogen, I am changing the forward reaction. Okay. Remember from our kinetics unit, the rate depends on the K value, lowercase k, not capital K, lowercase k, and the concentrations. So if I add more reactants, the forward reaction rate speeds up. Higher concentrations, more collisions, more reaction rate. So what happens when I make this change is that the forward reaction rate gets faster. I'm now creating ammonia faster than I'm using it up. At the start, it was in balance. The rate that the ammonia was getting created and the rate it was getting used up balanced out. That's why all the concentrations stopped changing. But with this change, with this disruption, with this stress on the system, I've thrown that out of whack. And so now the ammonia, the amount of ammonia is increasing. It's going up because I'm creating ammonia faster than I'm using it up. If the concentration of ammonia is going up, what's happening to the reverse reaction rate? More means more collisions means the reverse reaction rate is speeding up, right? So the higher the ammonia goes, the faster this one goes. And at the same time, the concentrations of nitrogen and hydrogen are going down, right? To create the ammonia, we're using up nitrogen and hydrogen. So what happens is the reverse rate speeds up and the forward rate slows down until we come back into balance. All right. So when you make a change, when you stress a system at equilibrium, the system responds, it reacts in such a way to undo, to minimize the change that you make. So when we added ammonia, or excuse me, when we added nitrogen, the system shifted to use up what we added. Okay. So when you add something to a system, it shifts away from what you add. If we were to take something out of the system is going to try and offset that. If you think about this and we say, okay, what if we do the reverse? What if I take nitrogen out of the system? What happens to the forward reaction when I take out nitrogen? Does it get faster or slower? Slows down. Lower concentrations. What happens to the reverse reaction when I take out nitrogen? Nothing. The reverse reaction is governed by the ammonia only. The reverse reaction rate depends only on the ammonia. If I affect the nitrogen, at that instant that I affect the nitrogen, the forward reaction rate slows down, but the reverse reaction rate is unaffected because taking out nitrogen doesn't affect the concentration of ammonia. It will change over time, but instantaneously, right at the start, the reverse reaction is unaffected. So what's happening now is I'm using up ammonia faster than I'm creating it. Okay. The amount of ammonia will decrease, creating more nitrogen and hydrogen, which will speed up the forward reaction and slow down the reverse until they're back into balance. Le Chatelier was the French chemist who first formalized this idea that a system at equilibrium will respond to any changes to minimize or undo those changes. So when you have a system at equilibrium and you make some sort of change to it, you stress it, you do something to it, it will react to offset or undo that change. Okay, that's formally known as Le Chatelier's principle. Essentially, a system, an equilibrium system, will shift to undo change. Changing the concentrations of chemicals is very clear. We can see how it directly affects the reaction rates. But there are two other shifts that we can do. Okay? We can change the volume of the container or we can change the temperature. All right. So let's go ahead and take a look at those two. The kinds of questions we're going to see about this just before we move on are typically like you have this system at equilibrium, you make this change, you add this stuff, you take this stuff away. What will happen to the system? Will I end up with more products or reactants, or which way will the system shift? Okay. So the direction of shift is the direction of what are we creating? Okay. So if I say, oh, I shift to the right, I'm saying I'm making more products. So I'm making more products. That's a shift to the right. Okay. If I say I am shifting to the left, that means I am making more reactants. Okay. So you have to keep in mind shift, which way you shift. That's the what you're going to be creating. Now, gases are affected by volume change. Solids, liquid, aqueous are not. If you change the volume of a container, it doesn't affect the actual volume of a solid, liquid, or aqueous substance. It does affect the volume of a gas. And because pressure and volume are inversely proportional, that means the pressure of each gas is changing. So when you change the volume of a container, you are affecting the concentration, the pressure of your gases. And that might affect the equilibrium depending on the ratio of gas particles in the reactants and the products. And the reason why I say it might affect this is because if you think about your equilibrium expression, products divided by reactants, if you have the same number of products and reactants on the top and the bottom, and let's say you, as in this example, I take the volume and I drop it in half, the pressure of each gas doubles. But if I have a single gas on the top and a single gas on the bottom, and I double both of them, top and bottom, the ratio stays the exact same. But I do have to take into account the coefficients because, as we know in the equilibrium expression, the coefficients become exponents. So in this example, when I'm taking nitrogen dioxide, which is this red-brown gas, it's a primary component in smog. When you visually look out and you see a smoggy day and it's this red-brown haze, that red-brown haze is nitrogen dioxide. It dimerizes, fancy chemistry word that means two small things bond together, into dinitrogen tetraoxide. Okay, this is colorless. I have a system at equilibrium. I've got a syringe, 10 milliliters, it's at equilibrium. I push the plunger down to 5 milliliters. Instantly, I have doubled the pressure of NO2 and doubled the pressure of N2O4, right? Half the volume, pressure doubles. But if you think about the equilibrium expression or the mass action expression and Q, the reaction quotient, I doubled the top and the bottom doubled, but then that doubling got squared. Okay. So when we think about our products over reactants, our mass action expression, a doubling, right, takes into account the coefficients as exponents. Because I have one gas particle on the right and two gas particles on the left, the top and bottom of my ratio are affected differently by changes in pressure. So doubled both, but the bottom went up by a factor of 4 because that doubling got squared. That means that the system is no longer in balance. Okay. A way to think about it is that when the pressure goes up, the system wants to undo that change. The system wants to have less pressure. It wants to go back to where it was. So it will shift in the direction that will produce fewer particles, lower pressure. So when we're talking about gases in a container, if you change the volume and affect the pressures, if you increase the pressure by dropping the volume, the system will shift to the side with fewer gas particles. Conversely, if you were to increase the volume, the pressures would all drop and the system is trying to get back to where it was. It shifts to the side with more gas particles. If the system has the same number of gas particles left and right, no change. There's no shift because we don't lose that balance of products to reactants. We stay at the same ratio. Okay. So changes to concentration, the system shifts to replace what you take away or shifts to use up what you add. When you change the volume, you look at the number of gas particles and the system shifts again to undo the change that you make. Pressure goes up, shift to get less pressure. Pressure goes down, shift to get more. None of these changes affect the value of K. The value of the equilibrium constant is independent of the concentrations, the pressures that we plug in. What it does depend on is the temperature. Okay. When you change the temperature, you change the value of the equilibrium constant, but it changes in a predictable way. Okay. If you are trying to predict how the value of the equilibrium constant will change when you change the temperature, you need to know if your reaction is endothermic or exothermic. And the reason why endo versus exothermic matters is because what's the effect you're having by changing the temperature is you're changing the rate constant. The rate constant, remember, is the Arrhenius equation where we have the steric factor and the activation energies and the temperatures and all that stuff. But because it's related to all those things that we learned about, if the forward and the reverse reaction have different activation energies, which they do, that means that they are not equally sensitive to the temperature changes. And the endo versus exo can tell us which side is more sensitive to temperature change. So when you're trying to predict what happens with temperature, you need to take into account whether it's endo or exothermic. Remember, exothermic, of course, means it gives off energy. We see energy as a term on the product side. And endothermic means that it is gaining energy, and we would see energy on the left-hand side. This reaction, as written, is exothermic. Okay. And what that means is that the reverse reaction has a larger activation energy and is more sensitive to temperature changes. The side with a larger activation energy tends to be more sensitive. But there's a quick shortcut for this problem. If you write down the balanced chemical equation and include the kilojoules, the number doesn't matter, just include the kilojoules on the correct side, exothermic, endothermic. You can pretend that changing the temperature is as if you are adding or removing kilojoules. If I increase the temperature, it is as if I am adding kilojoules here, and the system shifts away from what I add. More reactants, less products, K goes down. If I were to decrease the temperature, that is as if I'm removing kilojoules. The system shifts to replace what I lost, what I took away. That means it will shift to the right. More products, less reactants, K goes up. All of that is reversed if it's endothermic. Okay? Because you have to look at which side is K on, which side is the kilojoules on, because that's what you're telling. As a reminder, this is a as if, pretend. It's not what's really happening. Okay? Changing the temperature is affecting the rate constants because of the number of collisions that can meet the activation energy, blah, 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 all the stuff from last unit. And that changes the forward and the reverse reaction rates differently. But we can predict the direction of shift by thinking about it in terms of Le Chatelier's principle, as if, metaphor, simile, whatever it is, we're changing the amount of kilojoules. Okay. So we can see this actually taking place, right? You have some room temperature nitrogen dioxide. Okay. And what we do is we put them into different, we've got room temperature where they start, boiling water, higher temperature, ice, and a dry ice acetone bath, super cold. Okay. When you look at these, the color tells us the amount of NO2. At lower temperatures, is as if pretend I am removing kilojoules. So it shifts to replace what was lost. More NO2, more colorless gas, less color in the tube. When I increase the temperature, it is as if I'm adding kilojoules, shift away from what I add. I produce more NO2, darker color. Remember that changing the temperature will change the value of your equilibrium constant. Okay. More reactants, smaller constant, more products, larger constant. Question. It was just the way they made these tubes. I have no idea. It's unrelated to this. So again, when we're doing this, we are changing the rate constants without changing the amount of stuff. When I increase the temperature, the reverse rate speeds up faster than the forward rate. Then the system reacts by changing the concentrations to bring things back into balance. Yeah, it goes back to the exact same ratio. Not the same amount, not the same concentrations, but the ratios are the same. The new equilibrium is a different ratio, different K value. All right. One last question. One last question for you guys to think about. For our ammonia reaction, this reaction is also exothermic. Okay. I want you to don't say anything. I want you to think about this. If I want more ammonia, should I raise the temperature or lower the temperature? If I want more ammonia, do I raise the temperature or lower the temperature? Think about it. Talk to your neighbor. Talk to your neighbor. I want more ammonia. Raise or lower the temperature. So if I want more ammonia, what do I need to do? Lower the temperature. That's as if I'm removing kilojoules, shift towards what I remove, more ammonia. But if I lower the temperature, what happens to the reaction rate? Slows down. Okay, slows way down. This is the trade-off. It's a big issue when you're actually trying to design plants to do this. If you're trying to design a factory to make this, you want a lower temperature to get more ammonia, but then the reaction happens too slowly. That's where catalysts come in, right? Catalysts can speed up the reaction and we can lower the temperature. You do things like that kind of thing. Okay? All right. You've got a worksheet to do. Start with the worksheet. Once you finish the worksheet, hop onto the new active assignment for today. Hey guys, quick hint about this worksheet. It looks at first blush like a standard ice diagram problem, but it is a subtle twist. Yes, in part B, draw an ice diagram. Absolutely going to be helpful. But the total pressure is not the equilibrium constant. They are not the same thing. Okay. So you need to think about from our gas laws unit, what is the total pressure equal to? How does that relate to what you have in your ice diagram? All right. Give that a shot.